We can see the screen now, Professor.
Okay, I'm mute. Sorry. You can see the Spider-Man screen, am I correct?
Yep.
Okay, perfect.
Oh, yeah.
Okay, now I project. Okay. So I believe you, the last session is, you didn't stop here, but it's the last stop, okay? And we talk about the symmetric encryption. Just want to remind, okay? The symmetric encryption is the encryption where you use the same key to cipher and to decipher the message, okay? And follow the approach that we talked before. And we talk about this model is the Caesar cipher, and the Caesar cipher is a type of symmetric key. Why? Because you use only a key, the same key, to cipher and decipher, okay? And the model is very, very, very simple, okay? Just a moment. Yes. For example, shift 3 minus, in this case, you, for example, you get in the first is the plain text alphabet, you have A, B, C, D, E, F, G, H, and others, and you make a shift to the right, okay? For example, 3 shifts, 1, 2, and 3. Now A is D, and you continue the alphabet, okay? If you use the shift -3, is the opposite side, okay? You make the shift, but you make the shift for this side here, okay? Any questions about this process? No, it's very simple, no? So, just only to try a little, okay? It's you. If you have a pencil in a block of paper, if you want to use your computer, create a cipher alphabet, use the key equal 4 minus, okay? Follow, you try to cipher this message. The man is going to the mall, okay? Remember the space continue to be space, okay? You don't need you don't cipher the space, okay? You keep the space, okay? Can you do it? You'll do 5 minutes. I believe it's enough, no? Okay, 5 minutes to do it, okay, guys? If you have any question, I'm here, okay?
The line means which direction is going, right? The new alphabet.
The cipher alphabet?
I mean the line like after the 4.
It's the direction of the shift.
Okay, perfect.
Okay, everybody's finished or not? Yes? Juan, did you finish? Okay, perfect. So, just to click. Okay, did you see the Excel file? Am I correct? Yes? Okay, so it is the cipher alphabet, okay, EF, because it's 4 minutes, okay? And 1, 2, 3, 4, okay? A is E, B is F, and so on, okay? And when you need to cipher, is T. When it's T, is X, H. H is L, okay? It's a simple translation, okay? Any question, guy? Or everybody understood?
Sorry, I have one quick question.
Okay.
Can you please explain why it went to the, I think the left instead of the right?
Yes, because here, so I needed to get the page in a second. Okay, did you see here the symbol? It's the direction of the permutation. Did you understand?
Yeah, I think I did. Thanks.
Okay, perfect. So, any other questions? No? Okay. Where is my mouse? Give me a second. Okay. Now, again, the cipher is the same, okay? The cipher continue to is 4 minutes, okay? Now, you need to decipher this message here, okay? You already has the cipher alphabet. I believe in 2-3 minutes you can finalize it. Okay? You need to decipher this message here. Okay, guys? Start now. Okay. Did you finish? No? Okay. Okay. Mauricio, did you finish? No?
I think I'm very confused.
Okay, I believe are you clarify, are you show, and you can understand, okay? Just clean here, just a second. Update, clear, all right, okay. Again, you use the same alphabet, okay, the same cipher test, okay? And the idea, okay. The idea is to, oops, okay, stop. Okay. A little less. No. Okay. The idea is to do the inverse process, okay? You go for this line here, okay, the red one, and looking for C, okay? For example, COS, C is W. L, what is L? Well, is H. S is O, okay? Who? Space, M is I. W is S. Did you understand, Mauricio? You use the second line, the cipher line, and you make the same process. Then you use it in the because when you cipher, you get the letter here in the clear test and find the cipher test. When you have the cipher alphabet, you're looking for the cipher alphabet and translate to the clear test. Did you understand what I did? Yes?
Yeah, Professor, but something happened. Like I think in this alphabet, for some reason, there is no Y. I think I got confused because of that.
Ah,
Like
yeah.
you see X,
I missed
W.
one letter. Yes.
Uh,
Yes, you don't have the same letter in the order. Okay, okay. I missed one letter here. You are correct.
that's no problem. I
But
didn't.
again, in the next exercise, I missed it again. Okay. Use
Okay.
the alphabet and alphabet. Okay. Okay.
Okay.
Are you correct? Yes, you are correct. I missed the what is it? The Y exactly. So, but did you understand the process? Am I correct? Okay, it's an important thing. So, okay. So this one is a little different, and I will explain how it works. Okay. Again, I missed. Where is the Y? It's here. It's here. It's here. Oh my gosh! Where am I pointer? It's here. Where's? Oh my gosh, where is the Y? I see. Okay. So the idea here is you don't have the key. Okay. You don't have the key. And you have the cipher message. Okay. How to discover the key or how to discover the clear test message. Okay. Again, you don't have the key, but you know that this cipher message is wrote in English, and the cipher algorithm is the Caesar. Okay, you know only just two things. Okay, and you know that you don't know the key. How to retrieve the message, the clear test message? Remember, the Caesar cipher don't use any math operation. Use only permutation and transposition of the alphabet. Okay, create a new alphabet and don't use math operations. Okay, it's the first thing. And because you don't use math, you use the alphabet to create the cipher, only the alphabet to create the cipher. You can use, for example, a techniques in the cryptanalysis that the name is the frequency analysis. Okay? How to do it? Remember, it's in English. You can find in the internet the frequency analysis of the letter. What means this table? The letter E represent around 30% of the words that you use in the sentence in English. Did you understand? Okay. T, 9, A, around 80, O, until the Z, that is a less common word. Okay. This table is represented here, okay, in this graph. So, how to use this table to retrieve the clear test? The first thing, you analyze the cipher message and look for repetitions. For example, if you see here, which letter you have more repetitions? Okay, T, you have only one, am I correct? Z, you have only 1, 2. V, you have 1, 2, 3. X, então Z, you have 3. Okay? X, you have only 1. V already, no, Z no, V. Okay, it's not Z, it's V. F, have only 1. J, only 1. R, 2. D, 1. A, you have 1, 2, 3. K, you have 2. F, you have 2. K, you have 8. No, R, you 2. A, you'd have 3. And K, okay, K, you have 2. Oh, I already put it. Okay? Until here, it's okay? So what you need to do? Did you see here, you have V 3 times and A 3 times. If you reuse this table here, there is a good chance then the V and A is the letter E. What you do is replace V first and after A to letter E, okay? So I clear here to, I don't have paper to, or have, oh no, I have here, give me a second. Okay, V is 3, A is 3. Okay, what you do now is to replace. Okay, so replace V for E. Okay, E, E. What is it's V. Is E. If the alphabet, okay, if the letter V is Z, what is the key? You need just only to count, okay? I will simplify because I believe here just, okay. Don't see it, okay? But okay, if V is Z, you need only to replace the other letters. Am I correct?
Yes.
Okay, so WF. Again, this alphabet, you missed one letter, okay? Again, consider that this letter does not exist, okay? And you replace the alphabet, okay? And we'll decipher the message and see that it makes sense. Did you understand? Yes? Okay? It's simple. If we think that the V don't make sense, the message does not make sense, you replace the letter E, okay? And rebuild the cipher alphabet and check again that it works on our word. Did you understand the idea? Okay. In this case here, I create the clear test message cipher and create the exercise, okay? Yeah, just a moment. Okay, so, okay, it's the process, okay? You find the letter with more occurrence. In this case, replace V for E. If it's correct, what's the key? Okay, use the key and check if the message makes sense. If it's not make sense, you find the second more frequent word. Okay, remember then, this case is prepared to work. Okay, in the real, for example, if you get a big sentence, this relationship here, this graph here, make more sense. Okay, remember then it's a frequency of the alphabet. If you use only 5, for example, 10 words, it's more hard to find this behavior. But if you use, for example, to cipher a big message, it makes more sense. Okay, can you follow me? Yes, any question? Someone has any question? No? Okay.
I just got one question out of curiosity. The table of the frequency of letters is correspondent to the words, like the most frequent letters in all the dictionary, I guess, or something like that.
Yes, but in English, this table here is to English. Okay.
Okay.
Okay. Again, if you work very well, if you have a big sentence, for example, things that you have a page, a news in the internet, and you use a cipher, any cipher, okay, any key, sorry, any key, there is a very good chance that it's work. It's not work exactly, okay? For example, things that in this case is very simple, okay? But here you have 3V and 3A. If it's not work to V, you replace E for A. Did you understand? In some case, again, it's work to, because if it's not work to E, you can replace to T. Okay, it's a try, but it's work very well. There is another cipher model, is the, oh my gosh, Visionaire. Okay, in the Visionaire, it's a little more complicated. Did you know what is Visionaire? I believe I talked in the last class. Yes or no? No?
I don't remember.
Okay, maybe no. In the Visionaire, I will share, give me a second. I believe you see it now, my whiteboard, am I correct? Okay. In the Visionaire, you use a little different process, okay? Things that you have equal. For example, the Visionaire use a key. The key is a word, okay? For example, the key is, for example, alpha is the key. Oops. Alpha is the key. What it means? It means then, for example, I believe, give me a second. I believe if I share again my, okay. So where's my Excel file? Okay. Thinks the key in the Visionaire, for example, thinks that the key is alpha. Okay. What it means? Alpha is not a good password, but password is much better. Okay, it's the key. What it means? It means that you have, for example, you have a new alphabet for each word in the okay. For example, the first word in first word in any sentence that you have is this type of translation, okay? P, Q, R, S, T, O, V, and blah, 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 okay? The second, use the cipher test is the password is A, is continue, it's the same, okay? A, B, C, D, so on. The next one is S, S-T-O, blah, blah, blah. What it means? Things that I want to translate this sentence here. The general is in Paris, okay? It's the word that you try to translate, okay? What it means? The first was T. Oh, I need to continue. Give me a second. Okay, it's the same. Oops. Okay, if I want to translate to cipher this method, the T is J. The H is in the second cipher, okay? Is H because you don't have permutation. And the last one is the E. E is X. Did you understand or not? For each word in the password, you create a cipher table. Did you understand, guys? Yes, Mauricio. Okay, perfect.
Sorry, I have a question.
Okay.
So you make one with each letter, so there would be another table with W and then another one with
Yes,
O and
yes,
so on?
yes.
Okay.
It's much. It's a little harder to use frequency analysis. Okay, because remember, you don't know nothing about the key. You don't know the size of key. There is a way to broken this divisionaire. However, it's much more hard. Okay, and you can use, for example, cryptanalysis. To broken the divisionaire, the first step, you need to find the size of key. Okay, because you need to discover the size of key to try to, it's the harder part. Because if you find the size of key, you can apply the how to say, the frequency analysis like the Caesar one. Did you understand? In this course, it's not idea to spend time because nobody uses the Visionaire or the Caesar today. It's only to have to provide you one idea how the people work in the cryptanalysis in the past. Okay, it's only the idea. Any questions? No? Okay. Okay. So, it's the last part of the class yesterday, the class of the last week, okay? If you don't have any question, I will start the new topic, okay? That is more useful today. Okay. That the idea is to explain the symmetric blocks encryption algorithms, okay? Until now, we'll talk about the cipher, symmetric block, the symmetric ciphers, but you use only the class models, okay? Now, the word changed, okay? It happens after the enigma, okay? In this time, you start to use math to cipher message, okay? So the first part is symmetric block. What is a symmetric block? Okay, it is the most used symmetric algorithm because you have another one is the string symmetric string encryption. Okay, but the symmetric encryption you have a lot of advantages, but a lot of problems. The most used is the symmetric block. What is a symmetric block? You block the message, okay, in the specific size and cipher the message block by block, okay? What is the problem? The problem is things that you broke the message in 8 bits, for example, or 8 bytes, it don't matter, okay? If the message has 10 bytes, you have a problem because the first block it's full, but the second block you have only 2 bytes. Did you understand? And how to solve it? You use another operation. The name is pad. Okay, you pad. It's like the TCP/IP. Remember, the TCP/IP has the same problem. Okay, you have the specific field where you need to inject data in the package. And sometimes you have a few data than the package support, and you need to pad the package to complete the package to transmit. Did you remember in the TCP/IP? Yes? Okay, it's the same problem. Okay, if you one block, you have a message. I don't know the size. If the size of message in a specific time, the message is smaller than the block, you need to complete the block. Okay, the name of this operation is the pad. To understand the cipher, the symmetric cipher, one very important theoretical model is the FISTEL. Okay, a FISTEL is a symmetric structure. Okay, a lot of block cipher use the FISTEL. Okay, for example, GS, the Ghost, the Bluefish, and Twofish. Blowfish and Twofish is a very modern cipher model, cipher encryption. Okay, GS is old and the Ghost is old, but the Blowfish and Twofish, it's not so old. Okay, and use the FISTEL. The FISTEL model use the same algorithm to encryption and decryption. And the core of this model is the substitution and permutation operation. Why it's so important? Because it is very simple to implement and follow the design of the hardware board. Okay, these types, if your algorithms follow the FISTEL cipher, it's easy to implement in the hardware. Okay, because use only simple operations. Okay, for example, what is the substitution? For example, each plain text element or group of elements is placed for a cipher element. For example, use an exclusive OR. Okay. If you see here, give me a second. Oops. Okay. If you see here, oh. Okay. It's the plain text box, okay? And you divide these two plain tests in the left side and right side, okay? Most of the FISTEL use the same approach, okay? You receive a block, you split the block in two parts, and in one of these parts, you make a simple operation, the substitution operation. In this case, a exclusive OR, okay? And the permutation, you replace a sequence of words. For example, the permutation happened here. Did you see? You get this part, the right side, and send to left, and the left side you send to the right. Did you see or not? Again, I will replace. Oh. Okay, I will explain.
Sorry, I don't quite get it. Could you explain it again, please?
Yes, I will explain again. The FISTEL, again, the FISTEL is an idea. It's not an algorithm that you have, for example. You didn't find a FISTEL algorithm in any implementation. It's an idea, okay? A lot of algorithms use, for example, GAS use the FISTEL, okay? The core of FISTEL is two operations, okay? The first operation is substitution, and the second one is permutation. This part here represents the plain text block, okay? It's the things that you have, the message is, I will go to Paris, okay? And you want to cipher this message, okay? In the FISTEL, you define, okay, you have a block size, okay? You get the clear text message and broke and block. And one block, the first block, you need to process. And the first operation, you divide the first block in two parts. Okay, I will clean again. For example, the left part and the right part. Until here, did you understand? Yes or no? Okay, so, and you have two operations. I will explain the first, the substitution. What is the substitution operation? Okay, you receive the key, okay, and you apply in one function. Which function? The, in this case, exclude or function, okay? You get the left side and operate using the exclusive or if the round key. Do you understand until here? This part here, the left with the key. Okay? Yes or no? Okay? So it's the substitution. The second part is the permutation. If you, okay, are you clear to clean everything to become clear, okay? The permutation is, okay, in this time here, in this step here, what you have here, exactly on this point, what do you think? Is the left side short the key K1. Am I correct? Yes or no? Yes? Yes? Okay. And then the next operation that you have in the FASTL is the permutation. What is the permutation? You move this part here to here, okay? Okay. And you move this part here, that is the right side. You don't, the right part, you didn't do any operation here. Am I correct? It flow directly to this point here. Am I correct or no? And you move the right part to the left side. It is the permutation. Okay? Any questions until here? No? Okay, are you clear again to become clear? Okay. Now, what you have in this point here, guys, you have the right part of the block. Am I correct? Why? Because you go directly to here. Did you see the path? Okay. In this part here, what you have? You have the left part, short, the key K1. It's what you have here. Am I correct? Okay. What you do now? You make the same operation, but now the left part that you operate here flow directly to the right part. And the right part that you don't make any operation suffer the short operation if the K2. What's the K1, K2, and so on? When you receive the key in the FASTL model, you transform one key with a specific size in a set of keys that's required to make this operation during the process. Okay, you generate derivative keys to each turn in this FASTL model. How many turns you have? It depends on the hours that you implement the FASTL. Okay. Again, the FASTL is only a theoretical idea that a lot of algorithms use to work. And why the FASTL works? Because when you decipher the message, you follow the same model in the sorry, in the opposite side. You make the same operation. Remember the short, okay? The short is a reversible operation, okay? You apply the same operation in the opposite side, and you at the end you have the plain test. It's because it's so fast, this model, and so efficient, this model. Okay. The idea in this course is not to prove this idea. Okay. Again, but if you want, you can prove to you, not here in the class, but you make a session, you can discuss how it works. But it's simple to, okay, I'll just clear here. If you see this, understand this picture here, it's very simple to understand that it's work, because the only operation that you apply in this block is a short. Okay. And if you apply the short and the same key, you can, in the opposite side, you can regenerate the message. Okay, again, the firestone is only an idea. Any questions until here? No? Okay. Main ideas about firestone. First, the block size. Okay. The crypto designers use the firestone to generate the algorithms. Okay, GAS, 3DAS, Bluefish, and others. Okay, and need to consider this idea. Large block size mean greater security. Okay, how much bigger is the block, more security you have. However, the speed is the problem, because if you have a big size block size, you spend more time to make these operations. It's simple. You can measure in the computer. Try to make a short with 1 byte message, and try to make the short with a gigabyte message. You spend more time in the gigabyte message. Okay? So the key size. How bigger is the key, more security do you have. However, it's the same problem, performance. If you increase a lot this key size, you spend more time to cipher or decipher the message. Okay? Number of the rounds. You cannot use just only one single round, 2, 3, 4, 5. You need a large number. The typical size is 16. I ask you, why do I need a number that is not 1, 2, 3? Why do I need a bigger number? Try to explain here in this picture. What do you think? To answer this question, what is the security of this operation? You have only 2 operations, am I correct? Substitution and permutation. If you use only, for example, 2 or 3 here, did you see that it's simple to reverse, to try to find, it's easy. Remember the key of the cipher is the entropy. The entropy is the key of any cipher model. If you make only 3 operations, what do you think? The plain test and the cipher test is so different, or it's different, but it's not enough? What do you think? Come on, guys. Do you think that is, okay, you have only 3 operations. What do you think? The plain text and the cipher test there is a big difference, or a small difference?
I think it's a big difference. I'm not sure.
With 3 operations only?
I think that depends on the runs.
Depends on the meaning of rounds, exactly. Okay, because if you can do this exercise, it's a good exercise to do. Okay, because this operation is very simple. Okay, you can do it manually using the paper. Okay, things, for example, you have a small block, for example, 4 or 5, for example, 8 characters. Okay, and if you make this operation with 8 characters, you divide 2 blocks in 2 sides. The left side has the 4 first characters, and the second part is the 4 last character. Okay, and you can use a very small key too, just only to make this operation. When you apply this operation with only four rounds or 3 rounds, the cipher message don't suffer a lot of transformation. You don't remember, entropy is a statistic. Is a statistic attribute. Okay. Okay. In the statistic, you need to have a lot of operation. If you have a small, remember the idea of the statistic significance. Okay. If you want to use to calculate probability and other things, you need to have a big sample. Okay, because with a big sample, you can identify patterns. In the small sample, you cannot do it. You don't have enough data. You can. It's not exactly the same, but you can apply the same question to the Firestone cipher. This strongness of this Firestone cipher is the capability of this model to shuffle the data. Okay, but to shuffle the data, you need to have not a big number of rounds, but more rounds than 10 rounds. Because if you have a lot of rounds, the data is shuffled all the time. Remember here, remember the right side, you only permute it with the left flag. The operations only happen the left side. And now you make one operation here, okay? After you go to the right side. What happens? What is here? What is the result here? The result here is the right side with one operation, if you only one operation. To block the right side of the message, you only need to recalculate this part here, if you use 3. The left is a little more harder, because in the left, you have the first operation, you move to here. Here is clear, you pass, okay, you move to here. Here you pass to this part here without any operation, but you have one. And you make a second operation. Okay, the left you suffer 2 transformation, two substitutions. Okay, and the left is harder to find than the right, because the right only suffer 1 substitution. The idea to have 16 is because either the left and the right side suffer a lot of operations. Did you understand now? Mauricio, Rodrigo, Juan Carlos, okay? So I didn't see the others, okay? If the other has questions, Akana, do you have questions? Do you understand?
I understand.
Okay, perfect. Okay, guys. If anybody has any questions, please. It's not hard, okay? It's simple to understand, but a little different. So again, the number of rounds we already talked. The subkey generation algorithms, okay? It's the very important part of the Firestone model, because you have, for example, a key, and for example, 8 bytes is 32 bytes, it's not depend. You need to have a key with the same size of the block, okay? And if, for example, if you have 16 or 20 rounds, you need to have 20 keys, okay? If the same size of the half of the block, a half of block, okay? And it's important because you need to have a very strong model to generate the subkeys, okay? And the round function f, okay? Sure is a very simple operation. The good idea is to have something more complex, okay? But you cannot, the function cannot be so complex, because if it's more complex, you increase the time to calculate, to make the operation, okay? So, any questions? So the most common symmetric block encryption algorithms, the most famous is the GS, the triple GS, I will explain the both, and the AES. The AES don't use FASTO, okay? The AES use another math operation, is the, oh my gosh, what's the name is? It's the finite field, okay? And I will explain a little the math theory, but it's not the focus of our course to explain, because this type of math spend a long time to explain, okay? But it's not so hard to understand in the idea. The idea is, I will explain later about the ES, okay? But GS and triple GS use the Firestone model, okay? And the GS uses 64 bits of plain text. The cipher block is 16, and the key size is 56, okay? And the triple GS, you have a 64 plain text, 64 cipher text, and you can use a key with 112 or 168, okay? And the AES I will explain later, okay? So, the GS is the first. The GS is the first algorithm that is very important in the world, because it's a standard, it's data encryption standard. And it was created in 1977 by NIST. The NIST is an agency in the US that provides standards, in particular the security standards, okay? You have the cybersecurity framework, you have a lot of security standards from NIST, okay? And it published the specification of the data encryption standard. The name of the algorithm is the data encryption algorithm, GIA, okay? But the name of the model is GS. Again, the GS take a plain text 6 bits and a key of 56 bits to produce a cipher block of 64 bits. The idea of the model is this one. You receive a plain text with the 64 bits, and you suffer an initial permutation. This initial permutation, the reason to do it is to shuffle the initial data, okay? I don't know if I explained this course, but the idea of the initial permutation, it suffers the initial and the final. The idea here is to shuffle the data, okay, to start the permutation and the substitution operations, okay? And in the final permutation, the idea is to organize the block to be possible to reassemble and to reapply the opposite operation. Okay, so you divide the data in the 16 rounds, and you have the round key generator. Okay, you receive a 56 key cipher key, and you generate 16 key with 48 bits. Okay. Again, you have is the three operation: initial, file implementation, round function, and key scale. The round function is not a short operation. Okay, it's it's a little more complicated. Okay, remember, if you can see it here very easy. The block has 64 bits. Okay, in the initial implementation, you divide this block in two parts and shift these two parts in the left and the right sides. However, you didn't, the two parts is not the same size. Okay, how you do it? How you know about it? Because the key only, you make the operation in the key only in one part. The other part you only make permutation. Okay, it's the things that's a little different than the FISO model. Okay, so you create a lot of round keys, and at the final, you reassemble the data. Okay, remember, you make an initial permutation. Okay, it's not exactly the same permutation that you suffer in the FISO. In this case, you have like a table, and you make like the scissor table, and you make permutation. Okay, in between this data, and you make the data to left, to right, and you start the round one. In the round one, you make the two operations: permutation and substitution. In the substitution, you use a key with 48 bits, sorry. Okay, until you have the 64 cipher pass. The idea here, guys, is not to understand to have a complete understanding how this box operates inside. Okay, not in this course. Juan, Rodrigo, in another course, you'll understand better how it works in detail. Okay, but in this course, you don't have time to discuss in detail this type of model. The idea here is to understand why this model is so fast. Okay? Any question? Akana, Mauricio, Juan, Rodrigo said that is okay. Okay? The idea here, you apply these algorithms in the, I don't believe it today, but in the next class, you have an exercise when you can apply this model. Okay? But what's important here is to recognize the FISO model here in the GS. Okay? Any questions? So, why GS is not used today? The GS is not used today because not the problem in the model, in the algorithm. The problem is the key. The key has only 56 bits. Is so smaller key. To understand is, for example, if you have 56 bits, remember is 0 or 1 is a binary number, okay? The number of keys that you have is this number here. How many times you need to decrypt a message with this key? Use a brute force. Is bigger, but if you have a little better computer, for example, and cluster, any, for example, to broke it very fast, you can use a video card like NVIDIA, okay? That you can rent in a cloud, for example, okay? You spend only 1 hour to broke this code. It's very, very fast. Okay, it's the problem of GS. The new one, for example, AES, you use one example of AES is 128 bits. You need this increase. It's not enough, okay? It's close to the double of the key. You spend a very big number of years to make a brute force attack. In the AES, triple GS, you showed the triple GS now. You need to, brute force is impossible to do. You need to apply any other cryptanalysis method. Okay? Any questions? No? Okay. So because the size key of the GS, the people think, okay, we don't have the ES yet, okay? AES was selected in 2005 or 2006, I cannot remember. 2001, okay? The 2001, you select the ES, but you need to have a solution between the GS and the ES, okay? And the idea is to use a triple GS. What is the triple GS? It is, you apply a GS for 3 times, okay? 3 times. You apply one block GS, with the result, you reapply to GS, and if the result, you reapply to GS, okay? And the solution now is, you have a key of 112 or 168 bits. It's a big key, okay? And you fix the problem of the GS. What's the problem of this model? Who can say? What's the problem of the 3DS? The problem is in the picture.
That you have 3 keys?
No,
Or-
the problem is not the key. But the problem is the 3 times. The 3 is the problem, but what is the 3? It's simple, okay? Think here. What I told you about the GS. The GS is very performatic. Am I correct? It's simple. It's like you can design a hardware and apply you can design a hardware based on the GS, the Festo model. The problem here is, if GS is fast, now you need to apply 3 DS. It's not so fast. Am I correct? You apply 1 time, okay, you need to apply other time, you need to apply other time. You spend at least 3 times more than the normal GS. The problem in the 3D triple GS is the performance. Did you see? Yes or no, Mauricio? Can you understand? Juan, Rodrigo, Arcana, Diana, did you understand? The problem here is, if GS is performatic, is good in performance, the triple GS is not so good because you need to reapply GS 3 times. We spend at least 3 times more time, 3 times more, 3 more time to cipher our algorithms and to decipher. Okay. You have more security, but you spend more processor, you spend more time to process the message. Okay. So it's the problem. But the triple GS, you use triple GS for a long time. Okay. Until when? until you have the advanced encryption standard. The advanced encryption standard is the new encryption standard. It's the encryption standard that replaced the GS and the triple GS. What NIST did? NIST published an RFP and to select a new standard. And a lot of research in the world proposed the standard. And a committee of this evaluate the standard. I knew one guy, it's amazing because he's a Brazilian guy that's working in the group in the Sweden, in Switzerland, and he has the same name of me. Okay, Zé Barreto too. And he told me a little how this process happens. And the algorithms that he selected is the Hydro, okay? And it's a very, very, very efficient model, okay? It's fast and very secure. However, he didn't use the FAST model. He used finite field operations. Think finite fields like a math operation that you have a group, okay? A group of numbers. And in this group of numbers, you have specific properties, okay? One type of property is reversible, okay? In this group needs to be reversible. It's not so complicated operations, okay? But it's not so simple theory to explain so fast, okay? But it's not hard, but it's not simple to explain fast. But it's very efficient, okay? Why? Because it's you have a set of numbers that has specific properties that you can make operations, and the number in no time you have numbers that don't match the reversibility of the data, okay? So how GS works? Okay, GS use 120 bits to plain text or 16 bytes, okay? You organize these 6 bytes in the 4 columns and 4 rows for process as a method. It's the time that you make the math operations. You have a table like I have a animation that you can see it, but you have a table, okay? A specific table, and you use, for example, you get the data and you see the table. For example, the first bit is you change for the number in the table. You make operation in the table. The second bit you change for the second operation in the table, and so on. Okay. It appears a little magic, but it's not. It's a math operation. Okay. And the number of rounds is variable too. It depends the length of the key. You use 10 rounds for 108-bit keys and 12 rounds for 192-bit keys and 14 for 256 bits. Okay, and you use this key to generate a 128 round key. Okay. If you see here, the AES is very close to the FAST model. Why it's not a FAST model? Because this operation here, it's the only thing that don't follow the FAST model. Okay, the FAST model don't have these operations. Okay, but if you see here, it's very close. You have pre-round transformation like GS. You have the round 1, 2, 3, and you have the key expansion. Okay, in this case, it's a little different because in the first you operate the key to shuffle the key, generate the key. In this case, you increase the size of key to generate the round keys. Okay. The operations that you have The first one is the byte substitution, the sub-bytes. The sub-byte is you receive a 16 input bytes, okay, and you look up the pixel table S box, and the result is the matrix of 4 rows and 4 columns. You transform these 6 bytes in a matrix. These operations don't have in the FISTON model, okay? It's the difference. So after you make a shift rounds, okay, is a shift operation like the scissor to left, okay? Again, you get the plain text, you get the round key, and it's the first operation, and make the sub-bytes, shift rounds. You have a permutation too. It's the mixed column. You make a mixed column operation, and finally, you add the round key to make the operation, the final operation. So I have one video here. I just stopped to the share now. You need to reshare to share the audio. I believe it has audio. Give me a second. Oops, I wrong. Share again. Did you see this picture here with the video? Yes, guys, or not? I can't see you.
No, but yes, yes,
Okay,
we can see it.
because I cannot see you. I don't know why. I don't know why. Okay. So I will start, okay? Pay attention. Okay, and it's the hydro encryption, and you start to, okay, it's the first operation. And in this state, you have the block size, the plain text message, and you use the same operation in the state and the cipher key. Okay. Now we will explain the encryption process. Okay, if you remember, okay. I will stop
Sorry, Professor.
Okay.
There's like a black box in front of the screen. Oh, well, I don't know if everyone's having that problem. Sorry.
Okay, I will stop again. I will share.
Thank you.
Did you see now?
Yes, thank you very much.
Okay, I will back, okay? There is no sound, I will explain. Okay, again, it's the hydro, okay? It's the winner of the AES selection. And it's very important. You have the plain text, the cipher key, and you make the operation to create the cipher block. This picture here is the input. You have the plain text block message, and you have the cipher key. You make in the beginning an operation with these two datas to cipher the message, to prepare the data to the cipher. Okay, I will show here. Okay, I will stop here later. If you see here, you have the clear test and the cipher test. You have an initial round. The initial round, you add the round key, and combine the round key with the clear text block, okay? And you make 9 operations, the subbyte, shift row, mix around, and at the end, you get the round key and you combine it, okay? It's what you have until when? Until the final round, when you make only the subbyte and the shift round, okay? See the video. Okay, 2, 3, 4, 5, 6, 8, 9. And you leave and you make the final round, okay? You suffer 4 types of operations, okay? The first is subbyte. Remember this S box, okay? Its S box is a table. And you can think, oh, this table, how to generate this table? This table is generated from math operations, okay? It's not random, okay? It's not random. This box is not random, okay? You have some sense to create this table, okay? For example, 19, 1 and 9. Did you see? You get the line 1 and the column 9. And the 19 will become G4. And you do it for the rest of the block. Second operation, shift rows. Okay. You don't shift 0, 1, 2, and 3. And mix column. Again, you make a Galois field or finite field if you make this operation too. And you do it for each column. But you add the key. Okay, now it's explain the operation round to round. Okay. Now it's explain how do you do the key schedule. You have the cipher key and you apply the same operation, okay? You get a part of the key and make operation with the key. The same operation. You make the subbytes. It's like the clear test, okay? Okay. So, one second. So, okay. Why I explain this part to you? You need to memorize this operation? No, you don't need to memorize this operation. Okay, it's so complex, but it's important to understand how the algorithm works in the background. Okay, it's not magic. If you see, it's very close to the Firestone model, but the basic operation is not the Firestone. The difference between the Firestone and the AES model is in the Firestone, you don't have exactly you only permutation and substitution operation. It's very simple operation. In the AES, it's very complex operations. Okay, FUC. What is important here? The important part of this model is to understand the general behavior of this model and understand how to apply this model in the real world. Okay, and now we have only 30 minutes. Am I correct to finalize the class? Yes or no? Yes. Okay.
Yeah.
Okay. I will finalize here. And the next class, yes, thank you. In the next class, you will study the modes, the cipher modes. Okay, it's word it's the same to AES for any symmetrical cipher. Is, for example, remember the problem is the key. Okay, any problem. If you AES, you have a big key. Okay, but okay, it's not possible to make it's not possible to broke using a brute force, but you have a lot of other types to broke to discover the key or to discover the cipher test using, for example, clear test message. Okay, in the next section, in the next class, you study the how to increase the difficult to broke this code. Okay, how to do it? To use part of the cipher test to solve the key. Okay, what is solve? To make the key more hard to discover. Okay, I show one a very small example, but the next class I will back to this example. Okay, don't worry. For example, it's a type of the cipher mode, okay, electronic code book, okay. This model here is very simple. You have a block, you use the key, and you have the block cipher. The next block, you use the same key through encryption and the block cipher, and so on. The CBC is a little different, okay. You have the block of the plain text. You use an initialization vector and use a short operation in the encryption and use the key, and you have the block cipher. But if this block cipher, okay, give me a second. Okay, if you see here, the result of this part you use in the next blocks, okay. Using this type of operations, you increase a lot the difficulty to use any cryptanalysis model. Okay, what you see in this course, you will study only 3 or 4. Okay, it's not the most important, but 3 or 4 modes that is important to this course. Okay, but there are more than 12 modes of encryption. Okay, but did you see here? Did you understand why it's increased the difficulty to reassemble the key or reassemble the clear test? Yes or no? Okay, I cannot see you. Did you understand? No? The idea here, because I cannot see you, the idea here is, in the first model, okay, I go back. Okay, I go back once more. Okay, here is the simple model, okay? You use the same key in the all block encryption. Remember, here you have a block, okay? Oh, sorry. It's different. Okay, I go back here, okay? It's a block. You operate these keys. You need to schedule the key, operate, okay? The picture there is the complete block, okay? No. Okay. So you make it's the first model is here inside, okay? You get the block plain test, operate a key, but you use the same key all the time, okay? If you use all the same key all the time, the block cipher test, there is some patterns inside of the generation of the block cipher test, okay? In this case, the first key, okay, you start an initialization vector, is the same key, okay? The same key. However, see here, this part here is different all the times, because you use parts of the cipher to combine the block of plain text. I show another example. In this case here, you have initiate vector, the key, and encryption. But now you get the block of plain text is here, okay? In the second part of the operation that you apply with the plain text here, you use this part here and to improve the entropy, to increase the entropy here, okay? And you apply it all the time. So it's the reason that it's more hard to find patterns, because you modificate a little any process, any block suffer a different process with a different data. Do you understand now, Juan Carlos? Okay? Do you understand, Rodrigo, Mauricio, Akana, Diana, the idea? In the next class, you study this block, and I prepared a playbook in the Jupyter, and we'll do this playbook with you, okay? It's very simple, it's not difficult. The only thing that I asked you to do before is to install the Anaconda and the Jupyter. The direction is here. Give me a second. Okay, in the top 2 cryptology, you have the class today. You have a lot of information, and you have this task here, the lab 2. Oh no, sorry. It's not this talk today. I will install in the next one. This course today, you have an exercise, okay? The lab 2. The lab 2 is the cryptanalysis of the Caesar cipher, okay? To realize this exercise, you need to divide, to split in groups, okay, of 4. Oh, no, groups. Oh my gosh. Oh no, group of 3, okay? It's a 3, okay? One group of you, maybe you have 4, okay? You divide in groups and need to inform me by Slack what's the group organization, okay? Who is the members of the group, okay? Please select a name, for example, any name that you want, and this evaluations is until March, oh my gosh, March 12th, okay? It's a very simple, okay? You have a test, this test here, a cipher test, okay? You know that you apply the scissor, and you know that it's rotated in the Spanish, okay? In this link, you have the frequency in the Spanish, okay? And here you have a little more, another explanation about how to apply the frequency analysis, okay? This test here is not so smaller, okay? I see if it's open, yes. Okay, it's a big test, okay? Despite is a big test, okay? It's simple to apply because it's easy. It's the same way. You find the most frequent words in the sentence and apply the same approach that I explained today. Okay? Any questions? Okay, it's in group, okay? Please, only the only thing that I need to do until the end of the week is to organize the groups, okay? For example, Rodrigo, Juan Carlos, Diana is 3 guys, okay? It's my group. And the name of the group is blah, 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 okay? It's important that to enable that I create the groups in the Canvas. And when you submit the assignment, only one guy submit and the complete group receive the grade. Okay? Any questions? No? In the next class, you finalize this top and we work in with the playbook. Okay? Just remember, install the Jupyter playbook. The easiest way to do it is install Anaconda. Okay? Install the Anaconda. I send the direction tomorrow in the Slack, okay? To simplify the test. I send the links of the Anaconda and the directions how to install the tools to the next class. Okay? Any questions? This session, I record the session, I will publish in the YouTube and I provide the link in the Canvas, okay? And I share with you, okay? Do you understand everything? 8% of the class? Go
I
ahead,
have
go
a
ahead.
question.
Okay, I can.
The groups are going to be for all the semester or only for these
Yes,
activities?
for all the semester.
Okay.
Okay,
Thank
I
you.
use the same group until the end of the course. Okay?
Yes.
If you have any problem, for example, I count and I see that you are, I believe, 10, okay? But maybe, for example, there are one student that didn't make the quiz one. I don't know if it didn't make because didn't have time or because, I don't know, okay? If you have problem to the composition of the group, please send a message in Slack. I try to help you, okay? Okay, guys, thank you very much. I appreciate the time. If you have any question about this topic, please send a message. It's a pleasure to help you, okay? Don't keep problems in your hands, okay? It's simple, okay? It's a little hard to understand in the beginning, but it's simple in the general way, okay? Thank you, guys. Have a great night, okay? See you soon. I don't know, on Tuesday, okay? See you. Thank you. Bye-bye, guys. Appreciate a lot.